to take a very quick look at, where is it? Just in case you're wondering what this 2.2J is all about, this is on page 72, because this is kind of like a weird worksheet, all right? But it's kind of like, can you interpret the diagram? Yes? So if this is a rate diagram and we have H2 and I2 gives 2HI, page 72. I want you to think about what must have happened in order for that rate diagram to look like that. What had to have happened at time t? Yes, the system was stressed. See if you can figure out what the stress was. Was it a change in concentration? No, why not? Pardon me? Oh, you can change concentrations of gases. Okay. Yeah. The number of molecules on each side are the same. So that means it cannot be a change in now, okay. What if I said, is it a change in the concentration of H2? No, it's not H2 because both rates increase, and a change in H2 would only affect one of the two rates. So it's not a change in concentration of H2, nor is it a change in any of the other concentrations. Because that would only affect one of the two rates. Could it be a change in pressure? You should be talking with your partner. You should be saying yes or no, or I don't know, help me.
I don't think we know that the more we have to see, until we're not sure. We know that part of it. When we're ready for that.
Could it have been a change in pressure? No, why not? We have the same number of molecules on each side. Therefore, the rate would change the same amount. Now, if I asked you for an explanation and you wrote this, would I be happy? I should mention that they are gas molecules. Yes, thank you. Okay, that's why I left that blank there. So the answer is no. So what is left? Temperature. So there's only 3 different kinds of things we can change. We can change concentration, we can change pressure if we have gases, we can change temperature. So it must be, by process of elimination, a change in temperature. And what must have happened to the temperature? Must the temperature have increased or decreased? The temperature must have increased because the rates are increasing. Yeah. You don't have to, but I'm going to ask that. And that is actually a really good question. Which direction was endothermic and which direction was exothermic?
Would you say because forward is increasing more is
Because the forward reaction rate increases more, that must have been the endothermic direction. So that means if I was asked to put in the heat term, I would put in the heat term over here. Yeah? So do you see how you can get all of that information out of this graph? Right? And sometimes, you know, you get okay at drawing the graphs, but by analyzing them, it helps you give you a different perspective on them. Would you like to try one more? Should we try another one? Do you have a question? Why is heat on the reactant side? Okay, so if we look at our thing here, the forward rate increased more, right? Here's my forward rate, yes? And it increased more than my reverse rate. My reverse rate only increased that much. My forward rate went up like all the way, yes? Now, a change in temperature affects endothermic rates more than exothermic rates. So that's what tells us that the forward rate, the forward direction is endothermic. And if the forward is endothermic, forward direction must be absorbing heat, which means heat is entering. Yeah? Yeah. Cool. All right. Let's try the next one. Oh, look, it says at constant temperature. So it can't be a change in temperature. What happened at time t?
Pressure.
Is it a change in concentration? We just did this question. We did this exact same thing last time, right? In the last question. Could it be a change in concentration? No, because that would only change one of the two rates. And both forward and reverse increase. Could it be a change in temperature? No, because it says it's a constant temperature, right? So it has to therefore be a change in pressure / volume. What had to have happened to the pressure? Pressure must have, tell your partner, did pressure increase or did pressure decrease? The rates are faster, must have increased. Therefore, what must have happened to the volume? Decreased. Yep. Shall we see if we can find a concentration diagram and look and see if we can figure it out? Because we've got pages of these, pages and pages and pages. I'm not going to do all of them with you, but we're going to do a few of them together. Oh, here's one. Oh, this one's pretty easy. Page 78. Yes, sorry.
So what would the graph look like if it was the same?
If it was a change in concentration, one of the rates would go up and the other rate would stay the same.
That was the case.
If there was a change in concentration, because what it's going to do is if I increase the concentration of A, I would increase the forward rate. If I increase the concentration of B, I change the forward rate. If I increase the concentration of C, I change the reverse rates. So one of them will go up and the other one will stay the same. Or if I've removed something, if I've decreased a concentration, I could have one of the rates decreases and then comes back up, and the other rate will then meet it. So this would be an increase in concentration of something, yes? This would be a decrease in the concentration of something. The difference in the graph is which ones have no spikes? Well, this has a spike. It's only just one of them spikes. One of the rates spikes. Because if I increase concentration of A, I have more collisions between A and B, but I don't have any more collisions between C particles. So that would be staying, the reverse rate would be staying the same. So that's what we see here, is that the reverse rate does not change in that instant, but the forward rate does change in that instant. Did that make sense? Yeah? Okay. Any other questions before we move on to 3? You wanted page 78, actually, didn't you, Atrin? What number? Number 13? 15. Page 78, number 15. Whoa, look at this. Many things are happening here. Yeah, we'll figure it out. Okay. So we're going to tell the story of what happens at t equals 0, time 0. We place, what do we place in our flask? Well, give me a specific substance. Yeah, we put some F2. I need to really get this graph looking a little bit better. I need to go through and make the things a little bit. We place some COF2 and some F2 in a flask. Now, if I have 0.5 molar COF2 and I have 0.2 molar F2, which direction does this equilibrium have to shift? It has to shift to the right because I don't have any CO. The reaction cannot go backwards yet because I'm missing a reactant. Because I haven't put any of this in, that's at 0, right? And if I have 0 of that, which is what it says here, the reaction cannot go to the left. Okay, so I have to shift to the right. I have to be making F2 and CO2. And so, what do I see? I am making F2 and I am making CO. Yeah? And I am using up COF2. So at time t, we place some COF2 and some F2 in a flask. From 0 minutes to 15 minutes, the system is shifting which way? Right. Actually, from 0 minutes to how many minutes is it shifting? I lied. From 0 minutes to 10 minutes. It's shifting right. At 10 minutes, we have reached equilibrium. How do I know? Because at 10 minutes, those lines become flat. The concentrations stop changing. All right, so we're at equilibrium. That's nice. Now, what happens at 15 minutes? At 15 minutes, is the system shifting or are we stressing it? We're stressing it. What is our stress? Yeah, we remove some F2. That's our stress. And if you think about it, if you remove some F2, which direction should it shift? To the right. So we should be making F2. Are we making F2? Yes, we are. The F2 is going up. Yes? Are we making CO as we shift to the right? Yes, we are. The CO is going up. Are we using up COF2? Yes, we are. The COF2 is going down. If we shift to the left, we will be producing COF2. Does that make sense? If I'm going this way, what am I making? COF2, yeah? Yeah. So, where am I shifting? I'm shifting up till about, the curve seemed to flatten out at about 20 minutes. So from 15 to 20 minutes, the system is shifting right because we're making F2 and CO and we're using up COF2. At 20 minutes, we reach equilibrium. We reach a new equilibrium. Now, I would like you to chat with your neighbor and decide what is happening at 30 minutes. It is very important that you discuss this. What is happening at 30 minutes? What's happening at 30 minutes? Do you see a stress on the graph? Okay. Do you see a shift on the graph? Can you have a shift without a stress? No. There must be a stress in order to have a shift, but you don't see the stress on this graph. That means that the stress was not what? Okay, so the stress was not a change in concentration. Okay, because you cannot have a shift without a stress. Otherwise, if there was no stress, the equilibrium would be like, hey, I'm at equilibrium. Just hanging out here. Equilibriuming. Yes? So there had to have been a stress, but the stress was not a change in concentration because we would see a spike. In a concentration. Do we see a spike in a concentration? No, we do not. So you have three choices as to what the stress was. We've eliminated one of them. It is not concentration. You have two more choices. Discuss with your partner which one you think is better. Yes. That's correct. Now figure out whether it was an increase or decrease in temperature. How do you change pressure? How do you change pressure? You change the volume. So either you make the volume bigger or you make the volume smaller. What does concentration do if you make volume bigger or smaller? Does it change or does it not change? What is concentration? What is the unit of concentration? Concentration is measured in moles per liter. So if you change the liters, have you changed the concentration? Yes. So if you change the pressure, you have changed the liters. A change in pressure is due to a change in volume. Therefore, the number of liters change. Therefore, concentration changes. So what should you see on a diagram if we have changed the pressure? Spikes. All of them should spike. Let's just say for the sake of argument, I expanded the volume. Which way would the concentration of COF2 spike? Which direction would F2 spike? And which direction would CO2 spike? If we increase volume, decrease pressure, which way would concentration of COF2 spike, F2, CO? Chat about that. Now, before you get too excited, I want you to remember that I'm asking which way does it spike, not which way does it shift. So we're not talking about shifting yet. We're just talking about the spike. Is it going to spike up or is it going to spike down? If I increase the volume, what happens to the concentration? Decreases. If I increase the volume, what happens to the concentration? Decreases. If I increase the volume, what happens to the concentration? Decreases. Now, yes, you would have a shift. In which direction would it shift? It would shift right towards the side with more gas molecules, but that's not what was asked. We were asking about the spike. So they'll all spike downward, and then the F2 and the CO would come back up, and the COF2 would go down. Okay? Now, That's lovely, but that's not what we're looking at here, is it? So it can't be a change in pressure because all the concentrations would spike. So it's not a change in concentration that causes this shift here. It's not a change in volume pressure because we would see spikes. So what does it have to be? It has to be a change in temperature. Okay, so here had to have been at 30 minutes, we had to have had a change in temperature as the stress. Yes?
Earlier I asked if there like spikes when it changes
In rate. In rate. So it will change the rate immediately, but it doesn't change the concentration because just because the particles are moving faster means the rate of the reaction will be faster, but the concentrations will remain the same. So it depends on what type of diagram you're looking at. Does that make sense? Yeah. Good question, though. So at 30 minutes, the temperature must have been increased or decreased? So you guys are going to take a look at that. I've given you a delta H. You're going to figure out, did we increase or decrease the temperature? It is very important that you talk through this with your partner. Extremely important.
These are rates. Right? Going up and down. And then I get to here and I'm like, so that's got reverse. So now that's
One thing that it's always a good idea to do is to put your heat term into your equation. Does the heat term go on the left or the right? On the left. And which direction did the equilibrium shift at 30 minutes? At 30 minutes, the system shifted which direction? Shifted, the system shifted left. Why? Because we're making COF2 and we're using up F2, which means we must be going this way. If we're making COF2 and we're using up F2 and CO, we must have been shifting to the left. Now, Does that help you figure out whether the temperature must have been increased or decreased? Yes. Did we increase or decrease the temperature? We had to have decreased the temperature because the system then shifts to release energy to bring the temperature back up. Yes. Mm-hmm. And it is. It's increasing. Yes, because we're shifting to the left. Because my stress was a decrease in kilojoules, in kinetic energy, temperature. Right? The stress was a decrease in temperature. So we shift to the left, and that makes then more of the reactants and uses up products. It's about the stress. The uppy downy arrow is always a stress. The sidey arrow is always a shift. Well, you can treat temperature as though it is a product or a reactant. So we can treat the kinetic energy term as though it is a reactant. And if we decrease temperature, remember temperature is a measure of kinetic energy. So if we decrease temperature, we have decreased kinetic energy. So the system is going to shift to release more kinetic energy to bring the temperature back up again. Did that? Yeah? Okay. Anyone else want to ask anything about that? Yeah. No. Because you can see at this point what happens to the concentration of COF2 in that moment. Absolutely nothing. Right? Right here, nothing is happening to the COF2. So when we decrease concentration, it just sits there and goes, eh. But then we start, if the temperature was decreased, the reverse rate, I've got too many arrows on here. Let's do it in terms of rates rather than just in terms of shifting. Okay, my heat term is over here. Okay, so I have decreased the rate of the forward reaction and I've decreased the rate of the reverse reaction, yes? Because I've decreased temperature. Yes, I have decreased the forward more. So let's just say that this is, and the reverse is like this. So the reverse is faster than the forward. So what am I making? COF2. And look what happens. COF2 goes up because I'm making it. And the F2 goes down and the CO goes down because I'm using them up. Yes? Okay. Now, am I going to give you anything that complicated on your test? Absolutely not. Okay, on your quiz? No. Right? You'll get like one change. You'll get one graph. It'll either be a concentration graph or a rate graph. And I'll be like, what caused the change in concentration or the change in rate at time t? Yeah? So you can go through some of the rest of these, you know, on your own time. Okay? In the meantime, if we want to do a lab ever, we need to do 2.3. So let's talk about our KEQ expression. And we are on page 31. 91. At least it said it up there. Page 91. Do them on your own time. And tomorrow is the quiz. Okay, KEQ expression, page 91. Now, do you remember KEQ? What does the K stand for? Constant. Okay, so K is a constant. So as long as the temperature does not change, the ratio of products to reactants will not change. The ratio of products to reactants at equilibrium will not change. Now, if you're in the middle of a shift or at the beginning of a shift, that ratio is going to be different, okay? But the system is shifting to bring the ratio back to that constant value, okay? Brick? Where did the K come from? That's crazy. Bring the ratio of products to reactants back to that constant value. Now, one thing you're going to have to be able to do is to be able to write the KEQ expression or the equilibrium expression. And what you need for that is you need the balanced reaction. So we have coefficient A in front of reactant A, coefficient B in front of reactant B, coefficient C in front of product C, coefficient D in front of product D. How does this relate to our equilibrium expression? The equilibrium expression is the concentration of product C raised to the coefficient. Yes? Concentration of product D raised to the coefficient of D. Okay, don't worry, we'll do some examples. It'll be nicer when it's more concrete. Then we take reactant A and we raise it to the coefficient of A, and we take B and we raise it to the coefficient of B. So the coefficients of the equation become the powers in the equilibrium expression. Now, every time you work with a KEQ, you should be writing an equilibrium expression. Sometimes people get lazy and they stop doing that. You must write it. Now, you'll notice every one of those substances has concentration brackets around it. What sorts of substances can have a concentration? Gases can have a concentration. So we need to have substances that can vary in concentration. So gases are included because they have concentrations. Aqueous ions or aqueous gases have to be included because you can change a concentration. So gases, yes. Aqueous, yes. Do solids have a concentration? No. So solids, no. So those are not written in the equilibrium expression, and they will not cause a shift in a system. If you increase the amount of solid or decrease the amount of solid, you will not be shifting the equilibrium. Pure liquids. No. Now, number 5 is very rare. Very, very rare. So other than on this worksheet, you will probably not see this. But if you have A, which is a liquid, plus B, which is, I don't know, aqueous, in equilibrium with C, which is a liquid, you have 2 different liquids. If you have 2 different liquids, they can dilute one another. Therefore, they have concentrations. Now, how often does this happen? Not very often. It's a little complicated though, so we spend a lot of time talking about it. So people spend a lot of time thinking about it because they think it's important. But because it is very, very rare, it is very, very not important. Yes? The fact that gases have concentration, yes. Aqueous have concentration, yes. Solids have concentration, no. Liquid have concentration, no. Every once in a blue moon, you might see 2 liquids. It doesn't matter if it's in the reactants and reactants or reactants and products, because remember, everything in an equilibrium is in the same container. Products and reactants are in the same container. So it does not matter where those 2 liquids are, they can dilute one another, okay? However, like I said, very rare. If you just want to say liquids no, never, you'll be right 99.99% of the time, okay? And I can pretty much guarantee that on a test, you will not see a question with 2 liquids, because tests are sort of meant to be more like umbrella kind of things, application of concepts, rather than some stupid, picky little detail. Yes? And this is a stupid, picky little detail. All right. So let us take a look at this reaction here. So we're going to write KEQ equals, and we remember we want to have our products over our reactants. So KEQ is equal to, who is our product? C2H6, it is a gas, so yes, we include it. Concentration of C2H6. And what is its coefficient? Coefficient is 1. Therefore, do I raise it to a power? No. You could write a 1, but there's no point. Yes? We could write a 1. We usually leave off the 1. In fact, we always leave off the 1. So don't put it in. I just put it in there because it's our very first one, so you can see that it's got a coefficient. Now, those were our products. Here we're going to deal with our reactants. Should I be including carbon? No, because it's a solid. So carbon does not go in the KEQ expression. Okay. Should we include hydrogen? Yes. So we're going to put concentration of hydrogen. And what should we do with that concentration? We should raise it to the power of 3. Okay. One thing I want to make sure, never, never, never concentration of 3H2. What does that even mean? Are you wandering around collecting little triplets of H2? Oh, I got 3 H2s, 1, 3 H2s, 2, 3 H2s, 3. So I have 3 H2s. That makes no sense. Okay, you can't have a concentration of a multiple of something. Like that just, it's nonsensical. We're not going around counting triplets. All right, let's try this next one. What's the very first thing you should write? You should write K EQ equals. Excellent. And then we draw a line, and we're going to put stuff on the top, and we're going to put stuff on the bottom. Who goes on the top, products or reactants? Products. Oh, it's a solid. Do we include it? No. Oh, that was the only thing. If I don't have anything to put on the top, what should I put there? A 1, just a 1, okay? If there's no products with a concentration, just use 1. Have I explained that this means with? See, with the line over it means with. It's from the Latin cum, which means with. You can graduate with honors, cum laude. Yes? Okay, and so that is the abbreviation for with. I bring it up because I tend to use it without thinking about it. So that way you'll at least know what I'm doing when I write that, okay? So it means with. So we just have the 1 on the top, and what should go on the bottom? The reactants. So do we include lead? Yes. So we have Pb Why is there no charge? There should always be a charge. If there is a charge up here, if there were no charge up there, then you would not put a charge. But if there is a charge in the reaction, you need to put a charge there. All right. Concentration of 2Br minus. You guys are right. No, never concentration of 2Br minus, just concentration of Br minus. You should never have coefficients inside a concentration bracket. Just Br minus. Are we missing anything? Yeah, we've got a coefficient there for the Br, so we need to square the Br concentration. And look, we have now encountered a blue moon. Are you guys familiar with the once in a blue moon? It means something really rare. Okay, once in a blue moon, what happened here? We have a liquid, which would normally mean no, but we have a second liquid and a third liquid. We would only need 2, and that would mean we would include them. So KEQ, 3 liquids, therefore include. If it was 1 liquid, do not include. This is probably the last time you'll ever see this, okay? So we have KEQ is equal to products concentration of CH3, O, CH3. There's no coefficients, so we don't need to raise it to a power. My other product is water, concentration of H2O. That's a really weird thing to see. I should never see that again after today, concentration of water. And then on the bottom, we put our reactants, CH3OH, and we raise that to the power of 2 because it does have a coefficient. Is good? All right, so those are your examples. Why don't you guys try the first, like, 5? And then once you're done the first 5, you can work on 2.2H and 2.2I. So this is page 92. Numbers 1 to 5. Then work on 2.2H and 2.2I to prepare for tomorrow's quiz. I will be here after school today, and I will be here at Flex tomorrow if you want some help with this stuff, okay?
You're all right.
You can eliminate the 1. If you have a 1 on the bottom, you don't have to write it. In fact, it's kind of unusual to write a 1 on the bottom. We just leave it out, okay? Let me find those papers. Just online. So 2.2H and I are pages 67 to 71 all together, okay?
This movie, that movie on it. Okay, yes, You want to empty these?
Oh,
Would
you know,
that be helpful?
well, I have one of these.
Right?
I'm just wondering if there's an alternative. This
That one's been emptied. Okay.
Oh no, that's just a sweet. I'm just,
But we could WD-40 it.
no, that's okay. I have
Okay.
this one. Can I borrow this one?
Yeah, absolutely. Hi. No, it doesn't have to go all the way. It's not there if you want to wear it. Yeah. Once you reach equilibrium, just have it go on for a little ways. Yeah. Yeah. Hi. Okay, so we added some M2, so we're overgrading increases. You're right. Now we got this. Okay, yes, but we're just looking at leaves. Stop what's gonna happen to my forward days. What's gonna happen to my reverse days? So anytime there's a difference in the rates, basically they're just like one of the other than. So the rate diagram is actually pretty straightforward. If there is a difference. Yeah.
I know you call.
Yeah, because there's no point in stressing a system that's not at equilibrium, because it's already under stress, right? So yeah, it has to be equilibrium, otherwise that's complicated. It's like, oh, we're not at equilibrium, now we're further from equilibrium, oh no, what happens, right? So, yeah. You good? That's just not as much. Okay. Yeah, yeah. Yeah, it would go up and then. Yeah. So they're all the way down. Yeah. Because they're looking left. Okay, and so you're gonna be, these two will absolutely go down.
Oh, okay.
Yeah. Yeah. Hello. Okay. Okay, so what we have is we added M2, okay? So that increases, so your forward rate increases. And the reverse rate just stays the same in that moment, okay? And what happens then, the easiest way to do it is to say whenever they are different, whenever they're different, they want to round it up. So all we have to do. Oh. Okay, so what you're gonna do is. Yeah, except that, some of the increases both the reverse rate. And part of the moving faster. Yeah, and same thing for the reverse rate, forward rate, both of them. Okay, so they both stop, but we know we've been told that, endocrine rate increases in water. So our peak term would go here. Okay. So here's a peak term, so this is our endocrine rate, so it increases more, so that's where our reverse rate increases more. And then these two are going to, somewhere like that. Yeah? Yeah.
I think.
No problem. Yes. Yeah. All block 8, where have I put block 7?
How do I compare it our crossing count?
Pardon me?
How do I compare it our crossing count?
Inert gas does absolutely nothing to either diagram.
How do I?
You won't know if it's a concentration diagram, you don't know. So I couldn't ask you to say what happened. It would also be that you did nothing to the system. It could also be. Now, if it's a rate diagram, both rates go up for a catalyst.
How do I know if the substances in our graph are
Well, noble gases are inert gases.
just that?
Yeah? And I'll tell you if it's a catalyst. I'll be like, such and such is a catalyst. Yes. Now, why? What's going on?
I'm not ready. I'm not ready.
You're not ready. Why are you not ready?
Because I have 42 pages of practice I have to do.
You do not. No. You have 7, 8, 9, 10, 11. You have 5 pages of practice to do. 5.
You tell me, but
5. Okay? In the past, back in the day, I didn't have extra practice. There was no extra practice.
But I want to do it.
No, just go and do it. You'll be fine. It's one quiz out of your entire life. You'll be fine.
Spends.
You're not going to do 47 pages. Don't go and do 47
No,
pages.
42.
Okay, don't go and do 42 pages. Just do 5 pages. And then if you have a little extra time, you might be like, oh, I might do a little bit of the interpreting. Right? Just do the first few questions. No, you'll be fine. Off you go. Otherwise, I'll rip those pages out of your book. Hi.
Why does it, why, this is incorrect, why is the reverse rate, spike more than?
The reverse must be endothermic. Because
Right,
endothermic is affected more by a temperature change.
by any temperature change?
Yep, yep,
Okay,
Yep.
so it's not like endothermic, okay, so,
So an increase makes endo more high. A decrease makes endo more low.
okay. got
Yeah,
it. Okay,
yeah,
thank you.
yeah, yeah. Hi, you're looking for your test?
Yes.
Yes. It's in here somewhere. Let's just see. Half of these are upside down. Could you come back after school?
Yeah, sure.
Yeah. Why don't you come back after school and then we'll have more time, unless I find it in like the next few seconds. We'll do, oh, hey, there you go. Because I was a little worried it was going to be in like the pile somewhere. Yeah, okay.